Hi all, today we can see the problems based on ultrasonics. In the last video we have discussed about a piezoelectric effect and inverse piezoelectric effect. We have seen that the production of ultrasonic wave is based on this inverse piezoelectric effect. What is that? In some asymmetric crystals like quartz, tourmaline, etc., if we apply an alternating voltage in certain direction, then vibrations are produced perpendicular to that direction. If the frequency of this applied alternating voltage is matching with the natural frequency of that crystal, then crystal will vibrate with the maximum amplitude. That condition is the resonance condition. If that frequency of vibration of the crystal is greater than 20 kilohertz, the wave produced is known as the ultrasonic waves. What is ultrasonic wave? Ultrasonic waves are the sound waves which is having frequency greater than 20 kilohertz. For this sound waves to be ultrasonic wave, we have to apply the AC signal of frequency greater than 20 kilohertz. That frequency we can achieve with the help of an LC circuit. Using LC circuit, the frequency of AC voltage is F equal to 1 by 2 pi root LC. So by suitably selecting the value of inductance and capacitance, we can apply an alternating voltage of frequency greater than 20 kilohertz. Now, that AC signal frequency should match with the natural frequency of the crystal. So the natural frequency of the crystal is given by the expression F equal to 1 by 2t root of y by rho, where T is the thickness of that crystal material, Y is the Young's modulus of the material, and rho is the density of the material. So we can see some numericals based on this. First question is, find the thickness of quartz plate to produce ultrasonic waves of frequency 3.8 megahertz and 300 kilohertz, given the density of the quartz material. In this expression of natural frequency, the Young's modulus and density of the material remains constant for the same material. Now, the varying factor here is thickness. So, we can produce ultrasonic waves of desired frequency by suitably selecting the thickness of the crystal. So, in this question, we have to find out the thickness of the quartz plate that is required to produce ultrasonic waves of frequency 3.8 megahertz and 300 kilohertz. From this expression, what is the thickness of the material? T is equal to 1 by 2f root of y by rho. For the first frequency, that is for 3.8 megahertz, the thickness required is 1 divided by 2 into 3.8 megahertz, that is into 10 raised to 6 root of y. What is Young's modulus? 8 into 10 raised to 10 Newton per meter square divided by rho, that is density is 2650. On calculating this, we will get the answer as 7.23 into 10 raised to minus 4 meter. For the second frequency, that is 300 kilohertz, the thickness required is 1 by 2 into F is 300 into 10 raised to 3 root of y, that is 8 into 10 raised to 10 divided by 2650. So on calculating this, we will get 9.157 into 10 raised to minus 3 meter. That is, for the ultrasonic waves of frequency 3.8 megahertz to produce, we want a quartz crystal of thickness 0.723 millimeter. Whereas for 300 kilohertz, this thickness is 9.157 millimeter. That is, as the thickness of the crystal is decreasing, we are getting an ultrasonic waves of higher frequency. See the second question. Find the natural frequency of quartz plate of thickness 2 millimeter. Given Young's modulus equal to 8 into 10 raised to 10 Newton per meter square and density equal to 2650 kilogram per meter cube. Calculate the change in thickness required if same plate is to be used to produce ultrasonic waves of frequency 3 megahertz. So the given data is, we have to find out the natural frequency if the thickness is 2 millimeter. Now the Young's modulus is 8 into 10 raised to 10 Newton per meter square and density is 2650 kilogram per meter cube. So what is the natural frequency? F is equal to 1 by 2t root of y by rho. That is 1 by 2 into 2 millimeter, that is 2 into 10 raised to minus 3 into root of Young's modulus is 8 into 10 raised to 10 Newton per meter square divided by rho is 2650 kilogram per meter cube. On calculating this, we will get it as 1.37 into 10 raised to 6 hertz, that is 1.37 megahertz. In the second part of this question, we want to find out the change in thickness to produce an ultrasonic wave of frequency 3 megahertz. For that, we can find out what is the thickness required to produce a frequency of 3 megahertz. So, thickness T equal to 1 by 2f root of y divided by rho. That is T equal to 1 divided by 2 into the frequency we want to produce is 3 megahertz, that is 3 into 10 raised to 6 into root of Young's modulus is 8 into 10 raised to 10 divided by the density is 2650 kilogram per meter cube. That is equal to 0.9157 into 10 raised to minus 3 meter. That is 0.9157 millimeter. Now, what will be the change in the thickness required? So, change in thickness equal to 2 millimeter for the frequency 1.37 megahertz minus 0.9157 millimeter to produce 3 megahertz. On subtracting this, we will get a 1.0843 millimeter. So, to produce an ultrasonic waves of frequency 3 megahertz from this 1.37 megahertz, the change in thickness required is 1.08 millimeter. Next few questions are based on the applications of ultrasonic waves. Ultrasonic sensors have so many applications in medical field and industry. Ultrasonic sensors are used in sonography. Ultrasonic waves are used in sonar, that is sound navigation and ranging. In industry, ultrasonic sensors are used to find out the defects in the metal bars. To find out the depth of the sea under the ship, ultrasonic sensors are attached. And you have seen that ultrasonic distance meters are used to measure the length and breadth of the rooms in buildings. In ultrasonic distance meter, there is an ultrasonic sensor. That's a piezoelectric crystal, for example, lead, zirconate, titanate. That will send an ultrasonic pulse. It will reach the target and it will get reflected back. Now the time taken to send the ultrasonic pulse and to get received will get measured. From that we can find out the distance between 2 points. That is, speed is equal to distance divided by time taken. Now here what is the distance traveled? From the starting point to the final point, let the distance be d. Now the distance traveled to send the ultrasonic beam and to get receive will be 2 times d. So the distance d will be vt divided by t, where v is the velocity of sound wave. In air, the velocity of sound wave is 330 meter per second and t is the time of travel, that is time taken to send the ultrasonic beam and to get receive. See this question. A mild steel plate has a thickness of 18 into 10 raised to minus 3 meter. An ultrasonic pulse travels in it with a velocity of 5.9 into 10 raised to 3 meter per second. Calculate the echo time of pulse. So in this question, the thickness of the steel plate is given, that is the distance d. Now the ultrasonic beam is passing through this steel plate with a velocity of 5.9 into 10 raised to 3 meter per second. Now we have to find out the echo time of pulse. Echo time of pulse means the time taken to send the signal and to receive it back. So the time formula is T is equal to 2 times distance divided by speed. So 2 times distance is 18 into 10 raised to minus 3 meter divided by speed of the ultrasonic beam in steel bar, that is 5.9 into 10 raised to 3 meter per second. On calculating this, we will get it as 6.1 into 10 raised to minus 6 second, that is 6.1 microsecond. So 6.1 microsecond is the echo time of this ultrasonic pulse in the given material. Next question. An ultrasonic pulse echo method is used with a defective and non-defective steel bar of thickness 50 cm. If the pulse arrival times are 90 microsecond and 40 microsecond in the non-defective and defective bars respectively. Locate the distance of fault. In this question, we are using the ultrasonic beam to find out the defect in the material. That is, there is an steel bar, one is defective and another one is non-defective. This steel bar is having a thickness of 50 centimeter. In the non-defective steel bar, when we send the ultrasonic beam, it will reach at the other end and it will get reflected back. Now, if it is a defective steel bar, suppose there is a crack here, then ultrasonic beam will get reflected from that crack. So, in this non-defective steel bar, the time taken to travel the ultrasonic beam will be more, and in the defective steel bar, the time taken will be less. So here the location of the defective steel bar is here. Let that distance from one end be d2. The speed formula is V is equal to 2d divided by t. In both defective and non-defective steel bar, the speed of the sound remains same because the material is same steel. So, in non-defective steel bar, we can write the velocity expression as 2d1 divided by t1. Whereas for defective steel bar, the speed will be 2d2 divided by t2. Now, the speed V will be same for both non-defective and defective steel bar. That is, V1 is equal to V2. The speed of the sound in non-defective and defective bar is same. That is, 2d1 divided by t1 is equal to 2d2 divided by t2. We have to find out this distance d2. So, what is d2 from this expression? d2 is equal to d1 into t2 divided by t1. What is d1? d1 is 50 centimeter into t2 is 40 microsecond divided by t1 is 90 microsecond. On calculating this is 22.2 centimeter. That is, in the 50 centimeter thickness metal steel bar, there is a defect at a distance of 22.2 centimeter from this end. So, ultrasonic beams are used to find out the defects in the metal bars. Next question. An ultrasonic source of 0.07 megahertz sends down a pulse towards seabed, which returns after 0.65 second. The velocity of sound in seawater is 1700 meter per second. Calculate depth of sea and wavelength of pulse. Here the ultrasonic sensor is used to measure the depth of sea. So the depth of the sea is the distance here, that is d equal to Vt divided by t. V is the velocity of sound in sea, that is 1700 meter per second into time is 0.65 second divided by 2. On calculating this, we will get it as 552.5 meter. Next, we want to find out the wavelength of this ultrasonic pulse. What is the relation connecting velocity, frequency and wavelength? Wavelength lambda is V by F. V is 1700 meter per second divided by frequency is 0.07 megahertz, that is 0.07 into 10 raised to 6. On calculating this, we will get it as 24.28 into 10 raised to minus 3 meter. That is, answer is 24 millimeter. So, 552.5 meter is the depth of the sea and wavelength of the ultrasonic pulse sent is 24 millimeter. Next question. An ultrasonic beam of 1 centimeter wavelength is sent by a ship, returns from the seabed after 2 seconds. If velocity of ultrasonic beam in seawater is 1510 meter per second at 0 degrees Celsius. Its salinity at 30 degrees Celsius is 29 gram per liter. Calculate depth of sea at 30 degrees Celsius and frequency of ultrasonic beam. Here the ultrasonic beam is passing through the seawater. The salinity of the seawater is also given. The salinity is affecting the velocity of the sound in the water. The velocity of seawater which is having salinity is different from the velocity of the sound in pure water. There is an expression for the velocity of sound in seawater. This is the expression for the velocity of sound in seawater at t degrees Celsius. That is V equal to V0 plus 1.14s plus 4.21t minus 0.037t square, where V0 is the velocity at 0 degree Celsius, S is the salinity in gram per liter, and T is the temperature in degree Celsius. So what will be the velocity at 30 degrees Celsius? So V is equal to V0, that is 1510 plus 1.14. Salinity in gram per liter is given, that is 29, plus 4.21 into temperature in degrees Celsius, that is 30, minus 0.037 into temperature square, that is 30 square. On calculating this, we will get it as 1636.06 meter per second. Now, what we want to find out? The depth of the sea. What is depth of the sea? That is equal to Vt divided by 2. That is D is equal to the velocity of sound in seawater. Now we got it as 1636.06 into this time taken, that is 2 seconds divided by 2. That is 1636.06 meter. Next, we want to find out the frequency of ultrasonic beam. What is frequency of ultrasonic beam? F is equal to V by lambda. That is velocity that we got it as 1636 divided by lambda. It is given in the question 1 centimeter. That is 1 into 10 raised to minus 2 meter. That is 163606, or we can write it as 163.6 kilohertz. So in the question, if the salinity of the water is given, we can find out the velocity of the sound in the seawater using this expression, and we can find out the depth of the sea. One last question. A gauge meter which is calibrated against mild steel is used to measure the thickness of brass. The velocity of ultrasonic waves in mild steel and brass are 5.9 into 10 raised to 3 meter per second and 4.3 into 10 raised to 3 meter per second respectively. If thickness of brass measured by ultrasonic gauge meter is 15 centimeter, what is the real thickness? Here the gauge meter is used to measure the thickness of brass, but that gauge meter is calibrated not using brass, it is calibrated using the steel. Then the thickness measured is 15 centimeter, but this is not the actual thickness because the meter was calibrated using steel. If the gauge meter was calibrated using brass, we will get the real thickness. Now we want to find out what is the real thickness. The thickness of the brass calculated using the expression distance d equal to Vt by 2. V is the velocity of the sound, T is the time taken. So here the 15 centimeter thickness measured for this brass material is assuming this velocity of the sound as 5.9 into 10 raised to 3 meter per second. That is by assuming the velocity of the sound in steel. Now to get to the real thickness, we have to substitute the velocity of the sound in brass. For that, first we have to find out the time taken. So what is time? T equal to 2D divided by V. That is 2 into distance measured is 15 centimeter by taking velocity as 5.9 into 10 raised to 3 meter per second. Here we have to convert this 15 centimeter into meter, that is 15 into 10 raised to minus 2 meter. This is 5.085 into 10 raised to minus 5 second. Now to find out the real thickness, we have to use the actual velocity in brass. So real thickness is equal to Vt by 2, but this V is the speed in brass. So that is equal to 4.3 into 10 raised to 3 meter per second into time taken is 5.085 into 10 raised to minus 5 second divided by 2. That is equal to 10.93 into 10 raised to minus 2 meter. That is 10.93 centimeter. So this is the real thickness of the given brass material, 10.93 centimeter. So that's all about the numericals based on ultrasonics. Thank you. Bye bye.